This conference will now be recorded.
Hello, everyone, and welcome to the Satellite Book Club. We'll be getting started in just a moment with our presentation, but before we get started, we've got an announcement for you. As many of you are already aware, that the interleave period, the period within which those 18 ABI data was inserted into those 17 streams, both by the GRB and the SCMI, that's coming to an end today. Think about as we speak. The interleave has entailed populating the operational GOES 17 GRB, GOES rebroadcast, by interleaving in the GOES 18 ABI data, which doesn't suffer from the loop heat type issue. And so the GOES 18 ABI data was in the stream with the GOES 17 GLM and space weather data. That interleave started back on August 1st, and it concludes today as we speak. And it was a terrific mitigation for the August loop heat pipe period when the GOES 17 imagery was compromised at certain times of day. It affected not only the GRB, but also WFOs receiving the data from their SVN feed, the so-called SCMI. But with the transition today, we're switching back to GOES 17 and all the data pipes. Except for those developmental operations. There's a few sites that are looking at it via non-operational pathways, but the main operational pathway is GRB, and the SVN are going back to GOES 17 today. And the second interleave period will be held between October 13th and November 6th. And again, we're talking about GOES West only, to address and help mitigate the heat pipe issues that GOES 17 has been experiencing at that time of year. And then with that should be the last interleaving that's needed, the second and last, because by the time the next calendar year, issues might arise with GOES 17 ABI. We hope to be on GOES 18 by then. Wanted to pass along that update. And now let's get on with the presentation, but just a few more things. So the title of today's talk is the High Latitude Proving Ground Aid Satellite Research to Operations. Our presenter is Carl Dierking, Satellite Liaison and Developer for the University of Alaska Fairbanks, GINA, that's the Geographic Information Network of Alaska. And facilitating our talk today is Scott Lindstrom, Scientist Trainer from SIMS and SSTC. And we're glad and fortunate to have their expertise here for this talk. And as you heard a moment ago, this session is being recorded. As usual, we'll do the Q&A at the end of the talk. And we encourage your questions, especially from field staff, regional headquarters, WFOs, national centers. Please post your questions in the chat room, and Scott will help field them and respond to them with Carl. As usual, please sign in with your full names. Most of you are already doing that. Helps us keep track of who's here and helps us follow up with you if there's any questions. We are always looking for future presenters for the Satellite Book Club. Please contact the TOWS team. The contacts on the slide, and we'll re-show some at the end. And the training team can help create materials for your brief. Contact Brian Mata for information or questions regarding that. Thanks as always to the TOWS team, Kashad Bowman in particular, but the whole TOWS team, the OCLO, GOESR, JPSS programs, and again to our facilitator, Scott Lindstrom. A few words about Carl. Carl has been working with GINA since 2013. Before that, he was a SU at WFO Juneau, retiring after nearly 40 years with the Weather Service. He started at Forecast Office in Jackson, Mississippi, and later at the Hurricane Center. Didn't know that. That's quite a change. But spent the majority of his career at Juneau. And he's particularly interested in remote sensing and the meteorological impact of complex terrain. And on a personal note, Office of Observations has been fortunate to have had the pleasure to work with Carl on numerous occasions and hopefully continuing that in the future. Carl, welcome back to the Satellite Book Club. We look forward to hearing your presentation.
Thank you, Brian. As mentioned, I'm Carl. I work for GINA. GINA is a direct broadcast data provider. But in addition to that, GINA serves as a high latitude proving ground. And what that means and why that might be important to weather services throughout the U.S., not just in Alaska, is the focus of this talk today. Next slide. So prior to the launch of GOES-R back in 2016, Joint JPSS GOES-R Proving Ground was formed to bridge the R2O gap. Objectives were to utilize available satellite, terrestrial, and model data, emulate GOES-R capabilities to infuse GOES-R products and techniques into NWS operations, and to promote a dialogue between developers and users. And this was a great success. Many new products were available in AWIPS as soon as GOES 16 became operational. Proving ground activities, though, didn't end there, and they continue today throughout the U.S., not just in Alaska. And GINA was an active partner in this and continues to be. Next slide. So another event that occurred about the same time during that period was Hurricane Sandy, which exposed some preparedness issues with the hurricane, and a review team in the aftermath of the storm found that one finding was that greater access to LEO satellite data might have improved the timeliness and accuracy of the hurricane projections. So a supplemental was added to the disaster relief appropriations, and it had several objectives, but one of them was to deploy new observing systems, and the focus was on LEO data. This led to the purchase by the University of Alaska Fairbanks of an antenna named Sandy Dog, which was located at the NESDA's facility in Gilmore Creek, just north of Fairbanks. Next slide. So why is that important? Well, it laid the groundwork for satellite innovation, in particularly LEO satellite innovation, for the future. And the satellite talk by Brian and Vanessa last week, which was an excellent talk, kind of highlighted how ingrained in NWS operations geostationary data is, and the WSR-88D network is, but there are portions of the country where these systems don't work as well, and one of these is certainly Alaska. It's a large state, accounts for about a fifth of the U.S. in size, but it has a limited road system dependent on air and sea for transportation and commerce, which is weather dependent. But there are only really 7 88D radars, which take about 30 to be equivalent to the CONUS density. And geostationary data degrades exponentially in resolution and parallax as you head northward. Next slide. But the northern latitudes do have an advantage for LEO. There's a higher frequency of coverage because the polar trajectories pass near the poles with every orbit. And of course, with a low Earth orbit, the resolutions are much better. VIIRS I-bands are at 375 meters. The image in the center of the screen shows the pass frequency of VIIRS, SMPP at NOAA 20. So the colors represent the number of passes per day. And the orange box in the middle of the image shows that the northern portion of Alaska and the Arctic Ocean receives LEO pass coverage, these two satellites, 16 to 18 times per day. And even in the southern regions, the pass frequency is about 8 to 10 passes per day. But it takes more than high frequency. You need direct broadcast, which is receiving the data as the satellite is passing overhead. And then near real-time processing system. GINA depends heavily on the CSPP software package developed by SIMS to produce products that are delivered to the user within 15 to 30 minutes. It's also helpful to have multiple antennas. GINA is accessing up to 9 LEO satellites, and it's possible to have more than one passing within the antenna range at a time, and the more satellites, the less conflicts that are available. GINA has 2 satellites currently, Gilmore Creek, Sandy Dog antenna, which I mentioned earlier, and then we have a second antenna at the university campus we call Big Dog. We did have access to a third at one time at Utqiagvik or Barrow. It was a NESDA's antenna. It is a NESDA's antenna, but there are communication issues right now preventing access. If you step forward one, the image on the upper right shows that direct broadcast is not unique just to Alaska. There are several direct broadcast sites throughout the U.S., Madison and Honolulu and many others. So timely LEO data is possible throughout the U.S. Next slide. So with the additional Sandy funding and the new antenna, GINA was able to provide a suite of new single band products to the National Weather Service from direct broadcast. This table shows the LEO single bands that were comparable to what was projected for ABI at the time, and all these bands were delivered in late 2015. The pink boxes show the bands that are unique to LEO over ABI. The darker gray boxes show bands that weren't necessarily available. Missing, of course, for LEO are water vapor bands, but there are alternatives, which I'll mention later, such as microwave. Next slide. So with all the new single bands, addition to the AWIP satellite menu was added at the bottom of the Alaskan AWIPS menu, and it was for Alaska region imagery, which had several submenus for individual bands and for RGBs. Operations in Alaska for the Weather Service include more than just forecast operations. There's the Alaska Sea Ice Program, Aviation Weather Unit, and the River Forecast Center. Next slide. But operational use of direct broadcast data is also not exclusive to the National Weather Service. 2 heavy users include the Alaska Volcano Observatory. This is a consortium made up of the USGS, the University Geophysical Institute, and the State of Alaska Division of Geological and Geophysical Survey. And of course, a partner in this is the Anchorage Volcanic Ash Advisory Center, which is part of the Weather Service, the Alaska Aviation Weather Unit. For wildfires, the Alaska Interagency Coordination Center is a heavy user of the shortwave bands, fire bands, the fire detections. And this is made up of BLM, Alaska Fire Service, the Forest Service, the State of Alaska Department of Natural Resources, the Park Service, and the Bureau of Indian Affairs, and U.S. Fish and Wildlife. Next slide. So RGBs are very common now. We're very familiar with them, but during the pre-GOES-R days, they were not as familiar. Early exposure to RGBs were provided on SMPP, which is a LEO satellite, and MODIS. NASA Sport was an early promoter of RGBs using EUMETSAT recipes, and they did a good job of assessing the value. These are some of the more familiar ones that were very common today. And then in 2016, AWIP's client-side capabilities allowed the forecast offices in Alaska to start producing RGBs on the fly from the direct broadcast single bands that GINA was providing. And step 1. step forward just one here. And of course, even after the launch, RGB development continues. The fire RGBs developed by Curtis Seaman, the Dayland Cloud Fire and the fire temperature, are used, especially the Dayland Cloud Fire, are used heavily by the Alaska Fire Service for following the evolution of a fire, the fire perimeters, the smoke and burn scars, and so forth. And then more recent RGBs include the snow melt for snow characteristics, also developed by Curtis, and then a sea spray RGB by Bill Line, which kind of shows the strong outflow regions where over water, where there's sea spray. Next slide. Day-night band, very familiar. Everybody's familiar with it, but it takes special. It has special value when you have a lot of night, such as the high latitudes, and you get a very frequent number of passes. And this value was proven useful enough to be included as a recommended band for GeoXO. Next slide. What began in 2014 as a collaboration between SIMS and George Mason University researcher San-Mei Lee resulted in a VIIRS river flood aerial extent product. This was initially done at this in Madison using GINA direct broadcast data and the SSEC direct broadcast data. This product is particularly useful in Alaska for river breakup and has been used extensively ever since. It shows not just liquid water, but also frozen, where the ice is jamming and causing overflow of the banks. Where the water overflows is the red and orange view. Eventually, this processing was moved to servers at the university in Fairbanks for faster distribution, but an AWIPS product has been available for some time to the forecast offices here. And now, of course, it's available throughout the U.S. And if you step forward one, there's even a global product available in real Earth. Next slide. As I mentioned, with limited roads, aviation is important. GINA provides a couple of products that have gotten quite a bit of attention. The Snow Cloud Discriminator, which is kind of a novel multispectral product. It's not an RGB, but uses many different bands to produce colorized cloud layers, which help to discriminate the clouds from snow and ice. And in Alaskan winters, the snow and ice is white in this case. And so in Alaska winters, there's a lot of white. So this is a useful product to discriminate clouds and ice. Another package, the ClaverX Cloud Product Suite, produces a number of different cloud type products: cloud top height, cloud base, phase, type, and cloud top temperature and emissivity. This was the focus of an assessment by the JPSS Aviation Initiative to try and determine if that had value for pilots in Alaska. The initiative included a couple of pilot groups, which I've listed here, and the FAA. They were evaluating this package through geotips provided by GINA, and then an AWIPS product was provided to the National Weather Service. Three examples of this are shown along the bottom row. Next slide. An extension then of this ClaverX initiative was an application developed by Yuzhong No at CIRA. It's a web-based application, but it allowed Alaskan pilots to do a custom cross-section clouds, so they could draw their flight path and then get a cross-section of the clouds to expect along the way. Proved to be very popular for Alaskan pilots, and now is being implemented and expanded to the CONUS. Next slide. But there's more than just infrared and visible imager sensors on LEO satellites. Microwave is a very important sensor. The longer wavelength can ignore the small cloud droplets and actually see energy emitted from below and identify larger cloud raindrops. So, as I mentioned, with limited radar, having a satellite that can actually see through the clouds to where the heavier precipitation is useful. And if you'll step forward one and maybe toggle back and forth between that and the previous image, you can see that if you step back, in the microwave image, these cyan and blue colors are where the heavier precipitation are located, and you can see it doesn't really correspond well to the high cloud tops that are shown in the 11 micron infrared. And so this is the real value of the microwave, to actually see where the heavy rain is occurring and fill the gaps that are left by this limited radar network. We have several software packages. Rain rates are produced by CSPP MIRS package and also the CSPP gas package for AMSR2. NASA Sport provides rain rates from a GPROF algorithm, which is also available to Alaska. GPM rain rates, or GPM and GPROF from NASA Sport, were available to Alaskan forecasters in 2016, and the MIRS rain rates were available shortly after that in the spring of 2017 for National Weather Service forecasters. Next slide. So another microwave precipitation product, the snowfall rate, was developed by Quan Meng or her team at NOAA STAR. It was first distributed to Alaskan forecasters in AWIPS by NASA Sport, and then incorporated into the MIRS for the direct broadcast version. These two images are showing both rain rates and snowfall rates, so you can identify the areas of heavy precipitation, both liquid and frozen. There are some new features that are under development now, and a new assessment will be continuing this winter. And this product is also available in Real Earth. Next slide. Many other microwave products are available to National Weather Service forecasters. These are just a few, but the ocean winds from AMSR2, snow depths, sea surface temperatures, sea ice concentrations available from both MIRS and AMSR2, snow water equivalent and cloud liquid water, and so forth. Next slide. And of course, NewCap's very familiar. It's been around a while, but it has special relevance when it's available within 30 minutes and from direct broadcast. Using the CSPP HEAP package, GINA is also able to produce NewCap soundings from two additional satellites, the METOP-B and METOP-C. So with four potential satellites and the higher latitudes, there's some portion of Alaska with a NewCap's data nearly every hour, in some cases a couple of passes in 1 hour. And of course, AWIPS generates gridded fields when the NewCap's data is received, so this does include gridded NewCap's quite frequently as well. Next slide. I don't really have much time to talk about sea ice, but obviously an important hazard for Alaska, for navigation and so forth, and we have many products to address that. Next slide. We work with the NASA Direct Readout Laboratory on testing and showcasing some volcano products. They've produced the VIIRS Ash Index and the SO2 Index, and they also produce an SO2 product from OMPS. Next slide. And speaking of OMPS, which is the Ozone Mapping Profiler Suite, this is an additional sensor on VIIRS, on the NOAA 20 and SMPP. OMPS provides information about aerosols and trace gases, and the NASA DRL has provided a package that can produce an OMPS product for AWIPS, for ozone. Ozone is useful for diagnosing areas of strong potential vorticity or tropopause folds, areas of high ozone, and where these ozone areas are isolated, the potential cutoff lows, and low ozone might be indicative of blocking anticyclone. And if you step forward one more, of course, it can be used to calibrate the air mass RGB, which with geostationary data would be arriving much more frequently, but is subjective in terms of the coloring. So this OMPS ozone product gives you a quantitative value in Dobson units that you can apply to the coloring that you might see in the air mass. And step forward one more. And it also compares well to ozone from gridded new caps, which is also a field you can receive. It's might be difficult to see, but the blocky pattern on top of the ozone image that I had previously is gridded new caps, and you can see that it matches very well with what was shown in the OMPS image. Next slide. So with all of these new fields, the microwave and ozone and single bands, it added quite a bit of extra imagery to the satellite menu. And I know you're thinking, man, how does a forecaster look through all that? And in reality, they don't, because you don't need to look through every image every day. It's really dependent on what's occurring during that day and what your needs are. Nate Eckstein at the Alaska Regional Office started this process to create scenario-based menus that would help forecasters kind of zero in on the products that were relevant for a particular situation. Definitely more work that could be done in this area. And of course, forecasters also do their own organizing in procedures. Next slide. So the culmination of the work that GINA did in near real-time processing and direct broadcast came to fruition in 2021 when the GINA passed on the technology to the National Weather Service. The Sandy Dog antenna now feeds directly into the National Weather Service regional headquarters. They have near real-time processing servers, and so they're producing products that are delivered by LEM to the field offices. GINA still serves as a backup with the Big Dog antenna and an additional feed from Sandy. Next slide. And then GINA is supporting also ArcGIS mapping and cloud services. This is the method of delivery to the Alaska Fire Service, for example. And we're looking at future ways of delivering this data to non-AWIPS users. Next slide. So I hope I answered the question on why high latitude proving ground might be useful. Because it's an ideal environment for evaluating and applying satellite research to operations. And it's ideal because there's a great need. There's where there's a deficiency, people are saying, what are the alternatives? And let's take a look at it. As I mentioned, GEO and 88D have their limitations in this part of the country. It's a large state, but small population, so there's a close association with the user community for exposure and assessment and feedback. And of course, I covered the frequent coverage and low latency and multiple sensors, and over the years, a reliable method of distribution. So there's certainly things here that are transferable to other regions or to other sensors, and most examples I presented here were from AWIP screen captures. So that's it. Next slide. And if there's still time, I'm open to any questions.
Okay, thanks, Carl. Always interesting to hear what's going on up north. Just a couple of introductory comments. Please stay on the line for the discussion. You can enter questions into the chat, and I will read them. If you have a burning need to ask a question in person, that's also possible. Next week's Satellite Book Club on Thursday, September 15th at 12 p.m. It will feature Doug Kahn from the Forecast Office in Cleveland, and he's going to discuss the use of the MOSHI parameter. I believe that is the modified Sherby parameter to identify tornadic high shear low cape environments for severe weather. So please contact the Tower S team, either Lee Byerly or Kashad Bowman, for questions about the Satellite Book Club or for configuration for satellite products such as were shown by Carl today. So there are some questions in the chat, but I'm going to take the prerogative to ask the first question, and it's you mentioned the scenario-based menus that Nate created, which I think would be very useful. But are there this question gets to how does a satellite product get developed for being tested in Alaska? So if there's a scenario for some kind of event, who decides if the satellite product that's developed by someone is going to be included into AWIPS? How does that work?
Yeah, so right now it's very informal. It's the regional office has a Alaska test bed headed by Gene Petrescu, and any kind of new product is sort of run by the testbed group to see does this have value, and if so, let's take a look. Let's start to evaluate it. It definitely is missing a more formal review process, and after taking a look at this data, is it useful? But more than that, is it operationally significant? So right now it's informal, and as I mentioned, because of the need, there's a willingness to take a look at just about anything. But as more and more products get added, of course, there'll be limits. So at some point, a more formal review process would be needed.
Okay, thanks. We have a question from Bill Schoberg. Has the price of fuel for aircraft impacted the aviation community in Alaska? I'm assuming it has, but then he goes on to ask, it seems that it would put even more emphasis on optimizing flight planning to reduce fuel use. I guess to tie that into the direct broadcast, how easy is it to get for general aviation people to get the kind of information they might need from direct broadcast to help with their flight planning?
The application I mentioned by YJ at CIRA is certainly one of those. And one aspect where the price of fuel has really had an impact is with the fire service. They really have to consider the value of sending aircraft resources out to investigate a fire, and that's where satellite fire detections and fire imagery have become more and more important in their efforts. So in both senses, yes, the cost of fuel is definitely an issue, and the aircraft community is definitely interested in improving their flight planning in the process.
Another question from, I believe, Mike Jamalkowski. One of your earlier slides that had the table, you showed a blank for GOES fire band. I'm not sure which slide that was. Why?
Oh,
He wants to know why. There's no.
Yeah, there was a table, and so VIIRS has a 3.74 micron and a 4.0, and I showed him we provide both. One is an I band, one is an M band. For ABI, there's the 3.9. I cross-referenced the ABI with the 3.7, and I left a blank for the 4.0. But that was, there's one band in ABI and two in VIIRS. That's the only reason.
I guess I'll ask another question. Of course, geostationary data is always coming in, and you showed that there's lots of polar data, but are there specific times during the day over Alaska when you don't have polar data and you actually do have to rely on the geostationary for something that's evolving quickly?
I would say, first off, I'd say there is still a need for geostationary data. It's just that it's less. The resolution is less and there are issues, but there's still a need because of the high frequency. But in terms of LEO data, particularly VIIRS, there's a blank period between around 01Z and 09Z where the orbital trajectories don't cover the state. But then there are other satellites that help to fill that gap from Europe or the older MODIS satellite. Of course, MODIS is going away soon, and so there's a need for filling that gap, I guess, in coverage at some point. But yeah.
Okay, I don't see any more questions. I mean, I could ask Carl questions all day, but I could also just call him up. Here we have another one. For your slide on the VIIRS fire flooding, I saw no mention of the JPSS proving ground, which I thought helped at least in this development. But I think, Carl, you mentioned the flooding in, was it GINA?
Yeah, the JPSS proving ground was definitely involved. There's a river and river flooding initiative. Bill Schoberg leads that was kind of overseeing this. Sims and George Mason University, San May Lee in particular, were the developers in the project, but it was certainly a part of the river flood initiative.
Okay, thanks. And another question, this is from Kathy Strabla. Are you using CSPP polar to grid to create most or all of the imagery that you showed that is displayed in AWIPS? And are there other products that you would like to be supported by polar to grid?
Yes, polar grid is essential, and polar grid provides AWIPS products or creates the SCMI type AWIPS products that are used by the National Weather Service. So as I mentioned, CSPP, we use a variety of CSPP packages, and polar grid is a very important one in that suite of products that we do use. There's certainly a number of things I could suggest for polar grid, but right now we're just trying to make the best of the products that we are producing, and as I showed, there's quite a few products to kind of weed through. So we're trying to determine a little more what the most important products are and what should be supported operationally.
Okay. I want to call your attention to the link that Tristan has put in the chat for feedback. So please take the short survey for the Satellite Book Club. I don't see any other questions, and I know it's 4 minutes before quarter till, but I'll kick it back to Brian for some final remarks. Thanks, Carl.
Thank you.
Thank you, Scott Lindstrom and Carl Dierking, for this presentation. Beneficial to us here at headquarters, to the satellite programs, and certainly to the users as well. We have a sense that polar satellite data is underutilized, especially in other parts of the Weather Service. And so I think there's a lot to be learned from what the cooperative institutes and the autonomous regions have done. So thanks for bringing this to us. Very much appreciated. Quick update on the end of the interleaving for GOES ABI. As we talked about at the beginning, Lee Byerly, thanks for the confirmation that the GOES 17 was restored even as we met today. So that seems to be proceeding on plan. Just one more announcement, as repeating as Scott announced earlier, a week from today, please join us Thursday, September 15th, Doug Kahn from the Weather Service Cleveland office, WFO Cleveland. We'll discuss the use of the MOF parameter for identifying climatic high shear, low Cape HSLC environments. Thanks everyone for joining, and we look forward to seeing you again a week from today.